Okay, so once again, I'm Matt Cedarberg, CEO of Coreform. Greg Vernon, Director of Product Management, will be walking us through the item wizard, which makes hex meshing just a little bit easier in Coreform Cubit. So today we'll be introducing Coreform Cubit, introducing hex meshing, then we'll give a demo of how to use the item wizard on a few parts, and then have a Q&A. So whenever I'm coming into a new subject, it's always nice to know, like, those that are well versed in the subject, how do they feel about it? Like, what emotions should I have as I kind of come into mastery with something? So we did a poll at Coreform and asked some of our hex meshing experts here what emotion best describes for them the process of hex meshing apart. And there were a number of words that were shared, but we thought we could best represent this through emoticons. And these are generally the feelings expressed at Coreform with people that have made a career out of the hex meshing problem. There's generally not a lot of, I mean, there's, what were the words, Greg? Distress.
Anguish, pain.
Anguish, pain. Hex meshing, it doesn't seem to be anyone's favorite part of creating a model for simulation. That's the reason the item wizard was created, was to make this just a little bit better. And so we're hoping by the end of this webinar, and then when you have the chance to get in the item wizard yourself, your emotions may switch from these to more of an, okay, I've got this. And that the hex meshing can be a tenable part of your modeling process. We can't go on before acknowledging that this pain is exactly why Coreform exists as a company and why we acquired Cubit. We're creating a new solver based on isogeometric analysis, which really has been invented directly to address the issue of creating hex meshes. Once Coreform IGA is ready, hopefully later this year, then we expect the emotion surrounding this to switch even more to something like this, where hex meshing is just eliminated as a cause for consternation. So again, that's kind of our motivation as a company, is to eliminate this pain and to greatly accelerate and improve the workflow between CAD and simulation. But today, our goal is to just get you through for traditional modeling workflows. So a little bit about Coreform Cubit, if you're not familiar with it. It's a software that's been around for a few decades for advanced meshing for challenging simulations. There's all sorts of strong tools in the tool set, from CAD import to the semi-automated hex meshing that we'll show you today. Many Cubit users rely heavily on Python and scripting. Again, we've added IGA pre-processing to the Coreform IGA solver. And so if you're not familiar with Cubit, go ahead and grab a free trial on our website. Just a couple other plugs before we jump into the meat of the webinar, and I hand off to Greg. I guess first, the learning objectives. If you go ahead, Greg. We're talking about 4 things today. First of all, the big picture, like talking about like what shapes can be hex meshed. We'll go through some slides to explain that. Then when Greg goes into the live demo, talk through the gotchas, some common issues that make hex meshing challenging. Greg will reference all of the powerful Cubit hex meshing features, and then walk through the item wizard, which puts them all together in a nice, straightforward workflow. An item we'll define once and for all today means immersive topology environment for meshing. Let's call it the item wizard. Okay, so now just a couple other points. You can view all the webinars we've done in the past on YouTube. We do 1 or 2 a month. It's a useful repository. And then also just make you aware of Coreform Cubit Learn. If you're in academia, it's a way to get Cubit in the hands of everyone for free. The only limitation for non-commercial use, and there's a 50K element export limit. Okay, so this webinar is being recorded. Keep your questions coming in throughout the chat and the questions window, and we'll answer them back through the webinar. And with that, I'll hand it off to Greg.
Thanks, Matt. Yeah, I'm just excited to have seen where Cubit has come from, and I'm very excited for the future, as Matt mentioned, for things like Coreform IGA and just continuous improvement even in our Cubit product. So what I thought I'd do today is just talk about hex meshing. Why is it so challenging? We saw those emoticons earlier, and so I just thought I'd talk about fundamentally the challenge and why maybe hex meshing is a bit different than tetrahedral meshing, which we may all be aware of. We don't tend to have those same emotions around tet meshing because it seems to just work. And the reason why it just works is that when you're building a tet mesh, the only requirement is that you can build a bounding triangulation, as shown on the left, of your geometry. So if you can put a valid tri-mesh down, there are then guaranteed algorithms that can build tetrahedral meshes on the interior. And those meshes, especially in particular when they're linear triangles, can have guaranteed minimum qualities. And so tet meshing really is just a matter of building a fine enough tri-mesh so that you can put in a tet mesh. And we oftentimes might call this tet bombing, where we're just throwing a lot of tetrahedral elements at a problem to solve it. There are issues in simulation, in particular for nonlinear analyses with tetrahedral meshes and nonlinear analyses in structural mechanics problems, that they tend to be overly expensive and maybe challenging to converge to solutions. And so that's why hexahedral elements or hexahedral meshes are still, in many cases, preferred. So then the challenge, the corollary to that then is for hex meshing, if we have a bounding quadrangulation, as shown here on the left, there are no known algorithms. In fact, we don't even know mathematically if a quality hex mesh can even be produced on a given quadrangulation. And so because of this, hex meshing can't be fully automated like we can with TETs, and it requires a human in the loop to assist with identifying how to build a hex mesh. And that's really the fundamental challenge. It's an open mathematics question. But what we do have, and what tools like Cubit and other meshing codes have, is that they have found ways to build hex meshes on simple shapes, and shapes that can be described with a recipe. So in the left case, we have a general shape. It's a cube with one of the corners cut out with a sphere, as you might see like on an interior pocket of a mechanical part that then maybe has fillets. You oftentimes will get this kind of shape. This is the polyhedron mesh scheme in Cubit, which really is just a bunch of simple mapped meshes that get arranged in a certain manner to fill in that certain CAD topology. In the middle, we have a sphere, and there's a sphere hex meshing scheme in Cubit, which again is really just a decomposition of a sphere into 7 mapped mesh regions. And that becomes the recipe for building a sphere mesh. And on the right is kind of the workhorse of Cubit, which is sweeping, which is where you start with surfaces, either one or more surfaces, that are then, they're meshed, and then they're swept layer by layer towards a target surface, and slowly adding in elements as you go. And so really then what hex meshing is going to become, as we'll show, is the user trying to break their complex CAD model into some arrangement of these simpler shapes that Cubit or whatever meshing code they're using can recognize as hex meshable individually. But also, in order to do this, there's kind of like this larger algorithm that even as a human, we need to be able to actually even see those shapes or get to those shapes. And so there's kind of this workflow that if you've done hex meshing before, if you talk to folks who've done hex meshing, really it becomes kind of like a process where you go back and forth. But we start by importing our geometry. There's oftentimes some challenges or some issues with that geometry, so we might need to do some healing of that geometry. Sometimes the geometry is so broken that you have to actually go back to your original CAD application and maybe fix it there, and then come back to healing. And then once you've got it sufficiently healed, you might then do some defeaturing so that it can be simple enough for you to eventually decompose it. And again, you might find some challenges during your defeaturing, which require you to go back to healing, which may require you to go back to the CAD application. Once you've got it defeatured, you may then start decomposing your geometry into those small, simple shapes that we have those recipes for. But as you're decomposing, you might find that, hey, that's a feature that I need to remove because it's too difficult for me to decompose. So I might go back to defeaturing, and again, back and forth. And then finally, once you've decomposed it, you may go and you may build your mesh. And once you look at your mesh, you may decide, well, I could do some more decomposing to get higher quality meshing potentially. And so again, this process of cycling back and forth can occur. But this is generally at a high level, for those of you who are new to hex meshing, kind of the general workflow that you'll use in building a hex mesh. And this is kind of in regardless of whatever tool that you're using, but certainly this is common workflows in Cubit. So just to show what a couple of those steps mean, so this geometry defeaturing, if we have here a knuckle geometry, you can see that there are some small features like a small fillet here, as well as maybe a small face that is just offset from this cylinder, and it's tangent to a curve here. And then we maybe also have some small features that maybe I don't really care about, like these. There's a chamfer on these through holes, and there's also a chamfer at this top. And so defeaturing here, what we're doing is we're essentially throwing up a white flag and saying, hey, those are going to be too challenging for me to build a hex mesh on, and I don't need them for my simulation accuracy. So I'm going to remove those features wholesale. So I'm going to remove that fillet in the chamfers, as well as remove this little interior face. Again, this process though is a manual process that takes some time. Because it takes time and human time, it also takes some, it also can be expensive and costly. Then the next big step, and this is where these simple recipes I talked about come into play, is that whole geometry as a whole here on the right, it's not really a simple shape. I can't yet see, or the computer can't yet see, how to stack in these simple recipes. So what we do is we decompose this geometry into the smaller, simpler shapes that then Cubit can see how each of those shapes themselves fits a recipe. In Cubit, we call the tools that we use to make these decompositions, we call those web cutting in Cubit. You'll also hear this called partitioning in some other codes. But so as you can see here, again, this is taking a human going through either manually or with some tools to help them to find where those cuts are. And so again, that takes time, labor time, and takes money. And so any improvements we can make to these workflows that reduce the amount of time spent can save you or your company money. So now what I'd like to do is I'm going to switch over to a live demo portion showing the item wizard inside of Cubit. And while I'm pulling this up, Matt, I might just ask if any questions have come into the chat yet or not.
No, you're good.
All right, so I'm going to ask if people can see my Cubit application.
I can, yep.
Okay, good. So this is the Cubit meshing tool from Coreform. If you're not familiar with just kind of a general layout, we have a model tree here on the left, which will show us volumes as we're creating them. As we have things selected in our application, we'll have information shown up in this properties page. We have a command line interface tool here on the bottom where every single command that's done in the GUI has an equivalent command in our Cubit command language. And you can track what those commands are that you've run by down here in the bottom here, there's a history tab, which will show you a running log of those commands that you've run. And then there's also, from the default as Cubit ships, there's these panels here on the right. We have our command panel, which people who are experienced with Cubit will oftentimes use the command panel. So it's kind of maybe more of an intermediate to an advanced user starts to shift over to the command panel. But there's also tabs down here for item and power tools. If you don't see these tools, or if you don't see anything on here, you can make sure to add them by going to the View tab in the menu bar, and you can add or remove certain items. So for instance, I can remove the Properties page by clicking on Properties page, and it's now gone away. And so if you had your screen open and you didn't have Properties page, you'd want to come here and click on Properties page. And likewise, if you didn't have item, if item was not available for you, you would come into View, and then it's a little wizard hat with a wand is the icon, but it says item. If we click on that, item will show up, and we can then navigate that or make that the top item by clicking on its tab. So once you've seen this, or once you're in the item wizard, it kind of gives you a high level overview, which closely lines with the workflow that I showed previously. So this first little icon here, there are icons that go from top to bottom to kind of talk or walk you through the different steps of preparing your model. But they also are shown here as hyperlinks inside of the task description. So again, the first thing we're going to do is we're going to either import or create geometry natively, but in this webinar, we're going to just import CAD geometry. And it's walking you through kind of setting up and preparing this model. Again, the preparing being doing those healing operations, defeaturing, decomposing, and then we'll go on to meshing. There are also some, I've got a development build. So there's some links here that will bring you to the documentation in the production versions of Cubit, which will help you also understand the item wizard. So we'll start by clicking on this first hyperlink to import or create geometry. And that then brings you to this next panel where we can choose to either open a pre-existing Cubit project, maybe that one of your colleagues has provided you, or that maybe you created earlier and you want to just restart. In our case, we're going to import a CAD model from the file browser. But again, you could also build your own geometry. So if we click on the import a CAD model, while Cubit supports a lot of different CAD formats, here we're just showing a few of the CAD formats that are most common to Cubit. So for instance, we can import an ACES file, which is the native file for the geometry engine that Cubit is based on. But we also support step import. So I'm going to import this item example geometry, which you can actually find in the tutorials for Cubit. And it's now imported for me this assembly of 3 components. Once I've finished importing my geometry, I can click on the little done hyperlink at the bottom right of my item wizard. And if I keep on clicking done through these steps, it brings me back to my task description, and I'm ready to move on to the next stage. Now, this is a spot where if you wanted to get some initial kind of model sizing set up, we typically have budgets for how big your computer is and how many elements you can have just from a performance standpoint. We do support kind of setting your default, again, to tetrahedral meshing, which for many applications is quite valid to use tetrahedral for. And you can even put in like your element budget for about how many elements you want to have in your model. So say if you wanted to go down the path of tetrahedral meshing, we could say maybe put in 100,000 elements and apply that. And it would apply the scheme to prepare for tetrahedral meshing. But again, I'm going to switch back over to hexahedral as my default mesh scheme here. So now we're going to go on to the next stage. So we kind of done some of that maybe initial prep work. We're going to prepare the geometry. Now this little task within here has a button to run diagnostics on these different kind of 4 key things to fix invalid topology, which might be something that's where the healing aspect of Cubit would come in, but also to remove small features. And then we'll also want to make sure that our volumes or our mesh is well connected and that we have meshable topologies. So I'm going to run the diagnostics here. And so as we can see, it's gone through and it's said that these geometries are valid from a topology standpoint. So there's no need to heal this model. If we did need to heal this model, we would click on this hyperlink or fixed invalid geometry, and we could run the analyzer and then fix any issues that occurred. But again, this model doesn't have any issues. So we move on to removing small features. And we could select either all of the volumes in our model, or we could select just a few to then detect small features on. And so if I click on this, let's see, I might just want to, here we go, find small features. And the small feature size here is maybe 0.1. And so I can change my small feature size to 0.1 and then detect small entities. And so now if I expand these found things, it will highlight, in this case, I've got a small surface, so a small little fillet here, that, again, if I mesh this with hexes, you can imagine that to capture this really small fillet here, I'm going to have a small element edge to capture this. And that could drive down my stable time step if I'm running an explicit dynamics analysis. And that may make my model too expensive to run. And so I may decide that this is a fillet that maybe I don't care about. And so I'm okay removing this face. So if we select then one of those small surfaces in the small features window, the item wizard will show us possible solutions that we can use. And if we want to just simply remove this fillet, probably the best option for us to do, excuse me, pardon me, is we can look at removing this surface. And if I just click on remove surface, we'll see a blue kind of outline shows up and is previewing what the geometry is going to look like if I apply that operation. And so what you can see, hopefully, is that we've gone from this fillet to now we're going to have a right angle show up. So it's kind of like we're just extending the neighboring surfaces to remove this fillet. And you know what? That's what I want to do here, is remove this fillet. So I'm going to click on then execute. We can see now it's actually gone ahead and it's removed that fillet. I can then come back to my small features list and find another small surface. And if I look at this, maybe I don't see this. Maybe I'll click on a different one. I maybe don't see whatever this small surface is. So maybe I'm curious about where this is located. If I right click on it, I can get options that show me I can do like a fly in, and it will fly me into this to this small surface here. And again, so this is another small fillet that's going to drive down my stable time step for an analysis. And so I want to do that same operation of removing neighboring surface, or removing the surface. I'll go ahead and execute that. And I'm just going to make my graphics tolerance here. I'm just going to make my graphics a little bit nicer here, just so it looks a little bit better for us. We would go to another surface here. And again, another small fillet. Now, I could also, there are these small curves, which we'll see that these small curves correlate again to these surfaces. But what I like to do is whenever you have a small curve, see if there are any surface operations. So in this case, you can see there's an operation to remove surfaces, even though I've selected a curve. And so if I then choose to remove this surface, right, and there's a couple surfaces I could maybe choose. Sometimes it might say if I select a certain option, there's going to have some error because that's maybe an invalid operation. So it's not perfect, but Cubit is trying to help identify maybe operations that we could do, and we can select ones that work. So I'm going to select this remove surface 35, which should remove out this curve as well as a small surface. Yep. And then lastly, I've got, again, one small surface and some small curves. which I'm going to remove as well.
So Greg, there's a question from Ishak. He mentions there could be any number of small features. It seems like manually checking and removing all of them could take a lot of time.
Yeah, it certainly could. And that's, going back to our slide deck where we talk about that, this can be an expensive operation to do this manual cleanup. That's where, that is where there can be some challenges. Now, what I'll say is that once as a user, as you become more proficient at Cubit has a command language where what we can do is we can actually take these commands like remove surface 18 extend, and we can start to now maybe do some logic where we can say, I want to select all of these small fillets. So select these fillets in the using the command language, and then remove all those fillets using the command language. Since that's more of an intermediate to advanced tool here, I'm not going to talk about, we'll talk about that maybe in a future webinar about using the command language and some of the advanced options in Cubit to accelerate that. But today I'm just going to go in the wizard, and the wizard is very much like a one operation at a time sort of thing. I want to mention one more thing. So I increased my small curve length a little bit, just so we can see maybe some false positives. So one thing that Cubit's told me is that maybe there are some narrow surfaces. So Cubit has found that there's a narrow surface between these two curves, as well as it's found me some small surfaces if I fly into them. It's saying, hey, this is a small surface. And what I can do as a user is I can actually right click and I can mark this as okay. And then a little green checkbox shows up next to this surface. And what I want to show is if we go back to this, if we were to click on done, we'd still have a red exclamation mark around remove small features saying, hey, I am still finding small features. And so what we can do is that as we come through, we decide that these are features that, yep, this is a feature that I also want to mark as okay. There's a small surface here. Let's see where this is. Yep, you know what, maybe this is a mating surface with the next level assembly. Even though I know it's small and it's going to drive a stable time step, I need to still capture this. And so I'm going to mark this one as okay as well. Again, those two narrow surfaces were showing up here and then on the bottom of my geometry. And so I want to mark maybe I just want to mark all of these narrow surfaces as okay. So I can mark all as okay. And then I've got these small curves. Because these curves were associated with either a narrow surface or a small surface, because I marked those as okay, they automatically get marked as okay. And so now, if I click done, the remove small features, the box here will switch to all green, it's okay, because the small features I have said, yeah, they're small, but they're relevant and small.
So there's one more question. Why does it matter to identify small curves?
Yeah, so what can sometimes happen, I'm going to just create a curve here just so you can see this, is it will oftentimes happen in CAD applications. Let me go vertex viz on so we can see the vertices, is that you'll sometimes have a curve where maybe it has been split from some operation in the CAD application. So you might have a small curve like this. And if I were to say, again, I'm going to use the command panel here just to prepare this example. If I had, let's go like a size of maybe 1 here. So if I had a really large element size that I wanted to have, the way that Cubit and other tools that mesh CAD objects is they first mesh vertices and curves and they respect them. So because there is a vertex here highlighted right now, it's going to drive an element to be a small element length, which can drive a small time step size, but it could also create kind of this skewed element that's maybe a poorer quality than I wanted. And so as we're going through in the wizard, if I now select or look for small edges, it'll find this small curve for me. And then it gives me these options of what I can do. I can maybe, I can look at maybe like rebuilding the topology, and that doesn't quite do this preview here. That's not what I want to do. That almost has added more curves. I could collapse some vertices perhaps. So if I click on, I need to delete this mesh first though. So it'll allow me to collapse my my vertex. So let's go execute this. And you can see now that small curve was essentially taken to length of 0. So it kind of turned into like it was like merged in with this other vertex. But yeah, that's why you want to remove small curves. You want to remove curves that are smaller than you need for your analysis. And as well as small curves are oftentimes indicative of there being like a fillet. And fillets are notoriously difficult to build a hex mesh on. They can be done, but if you have 100 fillets in your model, if only one fillet matters, you want to remove the other 99 fillets that aren't important for your analysis and only have to worry about the one fillet. And that's why we're removing these. Yeah, that's a great question though.
Is it the radius or the length of the curve that matters?
For a fillet, it would be, I mean, the length would be equivalent, or not equivalent, but it would be proportional to the radius. But obviously, a fillet is typically like 1/4 of a circle. But we typically go by the curve length. But you are right. I mean, it tends to be just the fact that you even have a fillet at all that tends to be the issue with those. But again, generally, you're going to find fillets. Usually, they'll show up also as a small surface. But if you have a really long fillet, it may not. But the curve then at least might. So it's not an exact science. So there is a bit of art to this. So the next thing I want to show is this connect volumes. So here what we're going to do is I want to run a simulation where this is maybe like a steel header with maybe a pin on the inside of it or something, right? And I want these to be joined. And so we want these connected. But one thing we want to do first is see if there's any gaps or overlaps in our model. And so I can click on detect this, and it showed me that there's an overlap, and it's giving me a pair and which volumes are included. So again, if I click on the volumes, it'll show me those volumes highlighted. If I click on, or if I right click on the pair, I can then ask for it to draw the volume overlaps, which will give me this new kind of rendering. And here in red, it's drawn for me this overlapped region. And if I zoom way in, I can now see this overlapped region here. But maybe I'm a bit confused as what's going on here. So again, if I click on volume 1, I can see, okay, so volume 1 comes up on kind of on this little stair step feature. And I can see, okay, so volume 1's coming up to this red curve here at the top. If I click on volume 3, I can see, okay, and it came down to here. And so if I kind of toggle quickly between them, you can now see what that overlap is. I can reset my graphics, and now I'm zoomed in at this region, and lo and behold, there is my overlap. So now I've got some options for how to fix this, where I can maybe reduce a volume, and this reduced volume doesn't maybe really seem to do what I want, because it doesn't really seem to get rid of this overlap. I can also click on remove the overlap from the larger volume, which would be the green. And if I execute that, we can see now that overlap has now disappeared. And if I do detect gaps and overlaps, there are none anymore. So now I'm going to go to now imprint and merge. And so what this is going to do is if I look at the yellow volume and the green volume, so I want to have a conforming mesh, so a mesh that's joined at this interface. But if I draw this, there's no topology information on this yellow surface that there's a green body nearby it. So it has no knowledge of there potentially being a neighbor. So what we need to do is we need to imprint and merge some volumes. Again, it's found some volumes. I can change my merge tolerance if I wanted to. I can then maybe click on a given pair. Let me refresh my display here. And again, I can draw the surface pair with the volumes if I want to see what these volumes are. So this was this pair here between the purple and the yellow. I've got again, I can, if I needed to have some smart fixing, I might do that. But otherwise, I can just click on imprint and merge for all of these things. But watch what happens now. If I do imprint and merge for these volumes, if I now look at this yellow volume here, I've now got some additional curves that are sharing the topology of that green volume here. And that's important for making sure that my meshes align. So if you've forgotten imprint and merge, you'll have meshes that are disconnected from each other and you can't transmit stresses between them without using something like a tied constraint or a tied contact between them. So now I'm done with this step. I'm going to now, if I had contact, I could also identify these contact surfaces instead of doing imprint and merge, but we have no contact in this model. They're all imprints and merges. So I'm going to click done. And now I'm moving on to building a meshable topology. So this is a nifty little tool. I really encourage this for new users to Cubit, or even if you're trying to learn about maybe some advanced mesh schemes. I've actually learned using this tool, I've found myself some neat little tricks. So if we click on check meshability, we'll get two lists of volumes that are either meshable or not meshable. So, and this is based on previously when we did our setup FEA model, we said we wanted to build a hex mesh. Again, if we'd wanted a tetrahedral mesh, this geometry is already meshable for tets. But so I can click on volume 1, and I now have some options here for what I can do. I can maybe decompose this volume, that decomposition step we talked about. And so now this, again, the same list here, I've now got possible solutions that I can click on one solution, and then I can use my arrow keys to move up and down through the different solutions. And what we're seeing is for each of these, again, a blue surface, and we call this surface the web that's cutting, right? So this is why we call this web cuts, because this blue surface was coined a web a long time ago by the Cubit team. So maybe I want to apply this cut because I can see that it's going to cut along this inner radius. And that will make, it'll give me like a kind of a hollow cylinder here and then a kind of a sweepable surface. So I'm going to go ahead and execute. And what we'll notice is now in our meshable volumes, so I've got now volume 1, I've got this volume 3, I've got this other now volume 5. And those are all now meshable. Volume 2 is still not meshable. So we're going to look through here to see how we can mesh this. So I'm going to click on the first solution here and see what I can do. Now, what I like to do is, I don't always have to take the first option because there's oftentimes more efficient ways to do this. Because maybe I can cut all 3 of these little appendages off at once. And so if I just cycle through these, here's a cut that's going to sweep this surface down through. And so that will separate not just these 3 appendages, but from the yellow volume, but also separate this kind of cylindrical region from this yellow volume. So that's the web cut I want to do. So I'm going to go ahead and execute that. And now what we see is that all of my meshes are now meshable. And if I don't believe it, I can always just re-click on check meshability and double check. And yep, everything is meshable. Sometimes the web cut might cut off a little bit too much, and you might have to come back through and clean some stuff up by reuniting some geometries. But now I'm done with this step. I can rerun my check diagnostics. And now Cubit has now said, hey, I found some small features. So we talked about like going back and forth. So I'm just gonna like double check what these small features might be. And again, this is based on the small curve length that I just picked of 0.5. And so if I look at what these small curves are, I can fly in. And well, you know what? That's a curve. That's a small curve that I said I wanted in my model because I wanted to chop off this this gray surface. And so that's a curve that I'm going to just live with. If I want to capture this feature, I have to have it. And so again, I might mark as okay. And I'm going to presume that this is on the other side. Yep. And I'm going to mark this is okay. And I've got a few, again, small surfaces. And again, they're on those little appendages. So these are also all okay. And now we see that, right, now I'm all green. So if I'm all green, I'm ready to mesh. So I click done, and now I'm ready to mesh the geometry. And I can just select all my meshes or all my volumes, and I can generate the mesh. And I can double check how many elements I have. There's a command line option to, actually, I think I can actually select these in the monitor here. Let me just see if it'll let me. So I can right click and I can show quality, but I just wanted to see, let's see, list mesh info. And so I can see per volume, I can get some information about what mesh schemes might have been used. I think maybe it won't tell me how many elements I have. I guess if I do list totals, it will then list out for me how many elements I use. And so we can see here, I asked for 100,000 elements and I've hit right around 90,000 elements. So pretty good matching to my element budget that I asked for. So yeah, that's so now we've built this mesh. If I wanted to change off some of my mesh schemes, I can always select on a volume. If it hadn't meshed, I could choose a possible solution. I could go backstages and come back. Oops. Again, I've got a development build of Cubit, so my documentation is broken, but there are links that will help give you more information about what you can do. So I'm going to click on Done. Next, we might want to validate our mesh. And so I can define maybe the metrics I want or that I care about. So maybe I care about the size of my elements, which is maybe important for like an explicit dynamics analysis. And I can check my quality on these volumes. And so it's going to then show me here kind of my best elements, but also my worst elements here in red that I might want to look at from a quality standpoint. I can go back to my quality metrics. If I'm doing like a statics analysis, like a nonlinear statics analysis, I then maybe care more about how good the Jacobian is, because the scale Jacobian is going to tell me information about how easily my Newton solver can converge to a problem or to solutions. So then I'm going to check this mesh quality with the scale Jacobian metric. And again, the red elements are my lowest quality. So kind of see this looks to be my lowest element. But it's telling me that based on my criteria, none of my elements were bad because I have my minimum set to 0.5. If you wanted to maybe refine your mesh in a certain location, there are options to refine a mesh. And this will take you then over to our command panel. You could also delete the mesh.
So Greg, there wasn't a
Yeah.
question that came in if they wanted to just refine the, like say the yellow volume, if you turn off the,
Yeah.
like how would you do that?
Yeah, it's like this yellow volume here. So if we were to click on refine, so this will take us to this general refinement tool in our command panel. And at this point, I could then click on this yellow volume here, and I could tell it how many iterations to split it with. And there's some options I can choose, like maybe a target size is what I want to do instead. Here, my size is probably around, if I select my, I can select the little edge tool here, just select an element edge. Right, my length is right now about 0.45. So maybe I could choose like a target size of 0.2. And I could also do some post smoothing if I wanted by checking this box, but I'm not going to worry about smoothing. So if I click on this, I guess we can't mesh or refine volume meshes based on size. So maybe I'll just split. If I put this in by 1, that'll give me from 0.45 to about 0.2. Let's see. Depth option is okay, so let's see. I need to add volume 8 to my list. So I have to select multiple volumes it's looking like in order to do this. So I'll have to go through probably have to operate on my entire model it's looking like.
Is this because you merged them?
Yeah, it's because it's merged. And so refining the yellow volume is going to require a refinement of the green volume and all of its neighbors. There are things you can do like adding in like a sheet. So I could add a sheet between a few nodes if I wanted to like refine at a specific location. So there are multiple different options for doing this. That's probably why we said like this for volumes, maybe it's just to do all of those volumes with one iteration subdivision.
Okay, but if you had a solver that could take like non-conforming meshes, they just wouldn't merge. Is that right?
Right. Yep. If I was using a tool like Abacus that allows for tie constraint between the yellow and the green, and I didn't need to have this conforming mesh here, then I could have just refined the yellow. Yep. But this is one of the gotchas with hex meshing is that because those hex meshes, if we saw in the PowerPoint earlier, because these mesh schemes, you can see that they all natively have structure behind them. So hex meshing is really, even this swept mesh, there's a structure, right? It's structured in this sweep direction. You tend to get these refinements that then propagate throughout the geometry. So that's just that's why you tend to see that. And that's one of the benefits with tetrahedral elements is that them being natively unstructured kind of sets them up for being able to do local refinement a bit more easily than hex meshes do. Yeah, so I just want to finish up here. So I've validated my mesh. We have some options to set boundary conditions. And Cubit while it does have an option for materials and other boundary conditions, Cubit really is meant for is preparing certain surfaces or geometric entities for then a code like Abacus that uses sets as its definition. So I might make a node set that maybe is my, maybe I want like a reference point. Oops, so like a node set 1, I might call this reference point. And I might select a vertex on my CAD geometry. So I might select like this CAD geometry here, and then that will automatically pull any nodes that are associated with that when I export. I can select side sets, which might be what I do a pressure on. Or the code might let me do like a zero displacement boundary condition. So I might create something here. Maybe I'll call this X min. And I'll select maybe these X min surfaces by using control and clicking to select multiple surfaces. So for this coordinate symmetry model, I want to apply a symmetry boundary condition here. And so my model tree, I can now see that these items have been getting created. For time, I'm going to skip doing the Y max, but I'm going to come back and I can now define blocks which might be from my material. So maybe I've got block 1 and it's going to be called this pin. And it's going to be these 2 volumes here that I had that originally had been green. Another volume, I'm going to maybe just call this like gasket. And it's this purple volume. And then a third block that's going to be these remaining volumes. And again, I see those in my model tree. Oops. Oops. Looks like I fat fingered something. Here we go. Apply. Oh, and I gave it the wrong name. That's what I did. I got the name wrong. So let's just rename this to header. And so now in the item wizard, I'm done assigning my boundary conditions and I'm now ready to export my mesh to any of these formats that Cubit supports. So the native Genesis file format, which is another name for Exodus, which is the Sandia mesh format that's open source, and codes like Moose, the open source Moose applicate or code uses Genesis and Exodus. We want to export to Abacus or Ideas, Nastran, Patran, or LS-Dyna. And so I could choose to export one of these files and save it somewhere. And that's really using the item wizard. So let's go back to my slideshow now, unless there's any questions.
Yeah, there are a few. Go ahead and just finish up your slide because we've got just 5 minutes and we can answer questions.
So we want to, so what I say is I encourage you, as you move forward with trying to master hex meshing, there's a few steps that you can do. You can download the free trial of Cubit. We also mentioned the Cubit Learn as well, but you can sign up for your free trial here, which doesn't have any limitation on mesh export, but is a 30-day trial. Again, there's also the Cubit Learn, which is limited on export, but no limit on, it's not a 30-day limitation. We also have our tutorials on our webpage that you can walk through. And I really encourage going through the Cubit 100 and 200 lectures here. These are really good lectures that Sandia put together. And you can also join our user forum and ask questions here and get really responsive answers from the Cubit team and a lot of people with a lot of experience hex meshing. Yeah, and so now I'll go ahead and open up to questions.
Okay. Well, great. First, thanks again. You do an excellent job on these, and thanks for the time you took to master this and then to share it today.
Yeah.
Okay, here's a question from Ibrahim. How can you use hex 20, and how much would using hex 20 reduce the number of total elements?
Yeah, that's a great question. So the way that Cubit works is that, again, Cubit was based on codes being developed at the US Department of Energy National Laboratories. And they use this kind of logic called blocks, where in their codes, a block is what they assigned a material formulation to and an element formulation onto. And so once you create a block in the properties page, the block will have an element type based on, if you've meshed it with maybe a surface with quads, it will default to like a shell. If you meshed it with tets, it'll default to like a tet 4. We always default to linear elements just for speed. But if you click in this element type here, you'll then be presented with all these different element types that you can choose. And you'll notice here that these element types correspond to the Exodus mesh format, which you can find on GitHub. You can find documentation. I believe that their elements are compatible to Patran. So I believe that Exodus uses the exact same orientations and formations as Patran does. And so here we can find a hex 20. And so I could, if I redraw my mesh now, let me actually delete mesh. Let me do a coarser mesh here, just so we can see this more clearly. Oops, that's too fine. I want it a bit bigger. Delete mesh. Vol all size 5. Mesh vol all. Oh. Might need to reset those volumes in. I think the item wizard is all size 1 mesh vol all. Here we go. So this is a really coarse mesh here, but what we'll see is with this block, if I do like the header, if I change this to hex 20, you'll notice that the faceting gets a little bit finer. I can also draw node all, and you can now see these additional mid nodes showing up on my elements. Now, as far as how much that reduces the total number of elements, that's really simulation specific. And all that Cubit does is it just builds the mesh. But what I recommend that all analysts do, I mean, higher order elements do converge at faster rates than linear elements. So if you can afford to do that, that can oftentimes be a good option. In some analyses, especially like explicit dynamics analyses, there may not be a benefit to doing higher order elements because it cuts your time step down, and you get some robustness issues with regards to inverting elements that kind of have made linear hexes just the go-to for explicit dynamics analyses. But you can find that these higher order hexes can be pretty good for your for reducing your element count. And they are more efficient per degree of freedom, which is really what matters, more so than the number of elements. But yeah, that's a great question. We're looking to make sure that we can add more support for more element types as well. So I think in future releases of Cubit, it may not be immediate releases, but I think we'll see more options for what are available here. But that's where today you would change those element formulations.
Okay, Greg, I think we've got time for one last simple question. Okay. What's the difference between a side set and a node set?
Yeah, that's also a great question. So let me, maybe to make it even clearer, what I'll do is we previously created, let's now delete mesh, vol all size 0.25, just so we can see this. If I create a node set on this other face, let's create a node set here and call this Y max on these surfaces. What you'll see is that the node set is really just the nodes. And so oftentimes like boundary conditions are oftentimes just applied on nodes. They're just nodal degrees of freedom. And so all that you need to have out is what is the node ID inside of a boundary condition. What a side set gives you is for things like pressures that you're applying, you oftentimes need to have like the area of the element upon which to integrate a pressure. And so side set, if we zoom in, it contains the topology of those faces. And so it not only contains the nodes, but also, the element that they are corresponding to and their orientation, and then you can compute their size and Jacobians on that face. So you can do stuff like integrate a pressure over them. Oftentimes, a lot of codes will treat node sets and side sets effectively equivalent when it comes to like boundary conditions. So oftentimes, a lot of users will just use side sets for everything, because if they ever want to come back and apply a pressure, they don't have to redefine a node set as a side set. So I find node sets most useful for in my own workflows is I, again, use side set for all my load conditions and boundary conditions. I will use node sets for, I want to track the displacement of a single node, maybe throughout my simulation. And I want to maybe track convergence of that node as I refine my mesh. And that's what I personally use node sets for, is that they just become an output set for myself. So in this case, maybe I just want to track the displacement of this node. But it's a subtle how they're different. But if you want to apply pressures or integrated conditions, you'll need to have a side set.
Great.
So.
Okay. Well, great. Thank you again. Thanks everyone for taking an hour to attend today, and hope everyone has a great day.
Yep. Thank you, everyone.